Remember, we've been doing that. We did a bit on bolts last week. Hello, Connor. 1:15 we start. Happy Christmas. Bolts, when we did bolts last week, obviously the more bolts you've got, the more rivets you've got, the more area. Remember we did that? So if you want to bolt two bits of material together, you perhaps use a bolt or a rivet. Thought we started at 13:45. You've got to be better than that. You've got to be cleverer with excuses than that. I've come up with all of them before. Right, bolts. Don't forget, shear stress is still force over area. Shear stress, still force over area. Remember last week we did bolts and rivets. All right. So the more bolts you've got and the more rivets you've got, obviously the more holes you've got. But what makes 4 bolts better than 1 bolt? Can somebody tell me? What makes 4 bolts better than 1 bolt? More SA? Does that mean South Africa? More area, there we are. Because you've got 1, 2, 3, 4. So A, you've got more area. Because you've got this area here, if you remember. There's the bolt, so it's the area. Area of a bolt, pi r squared, things like that. So we've got more area. That's one good thing about it. And number 2, another good thing about it is, right, we could have the force. You could say that the force is divided by what? In this example here. We've got 4 times the area, or we've got, what could we say? If we've got 100 newtons, what could we say is on each? What could we say is on each? What force is on each? We could say that, yes, and you could, right? Not necessarily right, but you could say yes. We've got 100 newtons, we've got 4 bolts. Okay, well, I'm going to say then that we've got 25 on each. Because 100 divided by 4 should give you 25. So you've got less force per bolt. Not only have you got more area, you could do it that way. You've got more area, look, more area. Right. Got 4 times the area. Or we've got 4 times less of the force. That's why we have 4, 5, 6 rivets. Obviously, somebody made the point last week. The more holes you've got, the less strength you've got in the material. So you wouldn't go stupid. You know, you wouldn't have like 6 million rivets in a small bit of joint or small bit of metal. So we'll do a quick example just to refresh your memory. Here's my 2 bits of metal that I want to put together. We'll have a bolt or something down here. That's the bolt. That's the bolt. I'll draw it like looking down so you can just see what it looks like. That's the top bit, like that. Top bit there, and then the bit of metal is in there perhaps. And we've got, let's say, 1, 2, 3. 1, 2, 3. So we've got a force coming this way now. We'll have a force coming that way. Force coming this way. Oh, Gwilym. Force coming that way now, so I need a force. Somebody give me a force. Thomas Burbeck, give me a force. Any force, any number. Make it big. Thomas Burbeck, 77. 77 kilonewtons. Right? That's the force on this thing. Pulling both ways, right? Now, somebody give me, Alex Young, you can do this. Somebody give me a stress, like the ultimate stress that the bolt is going to break at. Like what? Might just give me a number. It's going to be megapascal though, right? So just give me a number that this bolt, whatever this bolt is made out of, this is the stress it's going to snap at, right? 100 megapascals, right? Okay. The only reason I'm doing that is because if we work out the correct stress, if it's more than 100, we're in trouble, right? So don't forget the ultimate tensile stress or the ultimate shear stress in this case, because we're in shear. The same thing though, right? Ultimate shear stress, 100 megapascals. So not the same thing really, but you know what I mean? It's the ultimate. So this thing, this bolt, this joint, the material is going to break at 100 megapascals. We've got 77 kilonewtons. We need to work out, is it going to break? Is it going to break? So we've got to do a bit of safety factor now. All right, got to do a bit of safety factor. So first of all, we've got to do this. Don't forget, we know that stress equals force, which we know, over area. So this will be our working stress. Whatever stress we work out here now is going to be our working stress. Hopefully it's going to be less than 100. Right? Because the material that Alex Young has picked is going to break at 100 megapascals. So we've got force. I need to give you area. How are we going to find the area? Well, you need to tell me, or I need to tell you, what size bolts do you want? Bearing in mind we've got 3 of them. What size bolts do you want? 5 mil. Okay. So Daniel Greenshields has gone to Spa and he's bought 5 mil bolts. We've got 3 of them, right? So the first thing we need to do is work out the area now. I'm going to go page 1, page 2. Right? We need to find the area, and it's going to be area times by what? Area times by how many bolts have we got? 1, 2, 3. 1, 2, 3. So find the area of 1 bolt. They're round, by the way, so that's cool, right? We've got 3 of them, so we'll times it by 3 and see what happens. So area. So we've got 5 mil diameter bolt. 3 of them. 3 of. Right, 3 of. Plus you don't like that, dear. You don't like it. That just means 3 of, right? So we'll do 3 of them. 3 bolts. Obviously area, so area is going to be pi d squared over 4. You can use that, or pi r squared. Area of a circle, it's up to you. Don't forget, 5 mil has got to be in meters, so 5 divided by 1,000. Because there's 1,000 millimeters in a meter. That's why we need to divide it by 1,000. So the area of 1 bolt is going to be this. Area is pi times by the diameter in meters, all squared, pi d squared over 4. Whack that in your calculator, and what you get? You should get something. First one to answer correct gets a Mars bar. I should really know this off by heart now. Then do 5 mil bolts on my fucking life here. What do we get? What do we get? What do we get? Sam Davis, Thomas Burbeck, Ty Richards, Max Barker, Lucas Banks. Come on, 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 come on. Give me an answer, give me an answer. Are you awake? Come on, come on, come on, come on, come on, come on. Am I talking Chinese to you? Give me the answer. 5,000. Somebody give me an answer. So I pick on somebody. I'm going to pick on somebody. Ty Richards, come on. Five divided by 1,000 squared times by pi divided by 4. 1963. Yes, well done. 1963 times 10 to the minus 6. Make sure you follow me because I'm going to pounce on people. Well done, Ty Richards. Meters squared. That's the area. Right, how many bolts have we got? We've got 3. 3 bolts. 1, 2, 3. So, to get the total area is going to be the area A times by 3. Because we've got 3 bolts. Somebody give me that. So 1963 times by 3 should give you a number. Is anybody going to give me the number? Before I ask Ty Richards to give me number out 23. 1963 times 10 to the minus 6 times by 3. Ty Richards, can you give me a number between 1 and 23, please? So I can count the register and pounce on somebody. Make sure everybody's listening to me. Any number, Ty? I'm going to count up and down. 7, right. Where's Ty Richards? I'm going to count 7 down. You're the bottom. Ty Richards. Right, let's go up. Let's go down. 1 for me. 1, 2, 3, 4, 5, 6. Dan Evans, you're number 7 from the top. Dan, 19.63 to 10 to the minus 6 times by 3. Have you got an answer, Dan? All we're doing is all we've done is work out the area of 1 bolt, which is 19.63 times 10 to the minus 6 times that by 3 because we've got 3 bolts. Daniel Evans, see what you get. It's coming, it's coming, it's coming, it's coming. There we are, spot on. 58, there we are. So the area, the area we're going to be using is 58.9. I will use that, right? 58.9 perhaps. Could use 59, can you? That's the area we're going to be using. 3 bolts, total area. So now, stress, in this place, shear stress is force over area. Force over area. What's the force? What force did you give me? 77 kilonewtons. Thomas Burbeck, don't forget the killer. 77,000. Right? That's the force. Divided by the area, which we just worked out. The total area, 58.9, something like that. 58.9 times 10 to the minus 6. That's the area. That's the force. This will give us the stress that this bolt is under, or this joint. So we've got the bolts are going to break at 100 megapascals. That's what we're saying, right? That's the route we've gone down. So, if this is below 100, we're in trouble. Now, there's other ways you can do this, boys, but this is the one we're doing. Right. Miles safe, aren't we? Miles. What's the answer? What's the stress? 1.98 giga. That'll do me. Right. So the answer is right because it's we got randomized. So your calculator will give you this 1.39 or 1.3 say times 10 to the 9. That's quite big, right? Or if you press, right, Sam's quite spot on, right? Or if you press E and G again, or right, 1/300, right? I'm rounding up now, by the way, boys, right? Times 10 to the 6 pascals. Right? Both correct. There's a reason why I've gone into mega, though, right? Tick, tick. Right? Are we in danger here, or are we going to live? I don't know. It doesn't look very good. Because we've decided to make this the bolt. We try to use a bolt that's going to break at 100 megapascals. Right? So these bolts are going to snap when we get to 100 megapascals of stress. Right? So the ultimate shear stress is going to break at 100 mega. But we're working at what our stress that we've calculated is what? That much mega. Are we in danger? Would you travel on this plane? Would you go on this bike ride? Would you drive in this car? Flipping no chance. It's going to break at 100 megapascals, right? Now the force that we've said is going to 77 kilonewtons. The bolts may be all right, right? We'll keep the bolts, but we may have to reduce the force a bit. Yeah, it's like Daniel Greenshields airline all over again, or Mansell Davis lorries, if you've read in the paper about Mansell Davis lorries. Apologies if anybody drives for Mansell Davis. See in the paper, I think they've got to close, I think. So, don't forget the safety factor. This will tell us now. Safety factor. Yeah, they've closed down Mansell Davis, yeah. Oh, they're going to close down because they were forging like MOTs, apparently. Been on for years, Mansell Davis. Safety factor, don't forget, is the ultimate over the working. Right? All that means is, what's it going to break at divided by what we're working at? This is what we're working at. So, some people have already seen it. So the ultimate is going to break at 100 megapascals. 100 times 10 to the 6. It's going to break at that. The stress that we're working at, this 77 kilonewtons on Daniel Greenshields airline is 77 kilonewtons. That's how much force, which gives us a stress of this. 1,300. So if you divide them together, that'll give you the safety factor. If it's below 1, we're in trouble. It's going to be massively below 1, isn't it? Massively below 1. James Bond. 0.0. 1/13th, yeah, you can do it as a fraction. All right, 0.07, 0.08, say that. That is why you shouldn't go on it. Anything below 1 is terrible, yes. This is well below 1, right? What could you do? What would you do? There's two things you can do. You either what? What would you do? You could either decrease that force, can you? Either decrease the force, buy stronger bolts, or put more in. Perhaps. It's up to you how you want to do it. It's up to you. You may not be able to perhaps put more bolts in. You may not be able to. What? 77 kilonewtons. That's why more bolts, more bolts, more bolts, more bolts. That's why a plane is full of rivets. To keep the safety factor high. Like. Reese Rivers is typing. That's one way you can do them problems, right? You don't need hundreds and you could need loads. You could work it out, can you? You could work it out. You could do that, can you? But if you found the area, you could do that. But you haven't got to do that. Now then, you may sometimes, you won't always get this. You're not always going to get, because it doesn't happen in real life. You're not always just going to get it nice like this. Right? You're not always going to get it with two bits of metal like that and a bolt or a rivet like that. You're not always going to get it where you've got a force going this way and a force going that way. Because sometimes, as in normal, you may get a force coming this way, right, straight down on it as well, actually pushing on it. You may also get a force pulling on this bolt as well, in real life. You also may get a force perhaps going like that. You may get a force going like that. Don't forget, if you've got a force going like this, like we did in vectors, you've also got, this is going to be, there's going to be a force going this way and a force going that way. Huh? Obviously, I need to give you the angle. Right? So, let's see what happens when you do that. I'll give you this example. Right? Because you've got to do a bit of maths now. Okay, using, remember we did this? F cos, F sine. This may give us the horizontal component, if you remember. And this may give us the vertical component, if you remember back that far. So, you could have an example like this. Let's do it on, we'll do it on here. Let me just rub out this bit here. Let's rub out all this bit here. You could end up with a bit of metal like this and a bit of metal like this. Put them together and we could have a bolt or a rivet in there like that. You may also have a force just pulling on it like this. All right, I'll just draw it roughly. That's all we've got. We've got a force pulling like that. Okay, so we need to work out what's the force in the shear direction there, and what's the force, right, the direct force. So if I've got a force like that pulling on that bolt, let's say, somebody give me a number, somebody give me a number for force. This resultant angled force, 200. Flip it out. 200 Let's go really, really big, shall we? 200 kilonewtons pulling on this poor bolt. Bless it. Huh? So that there is the force coming in this direction. Now we don't like that, do we? Because we can't do a lot with it. We need to convert it. If you remember, don't forget, every resultant force, you can break it down into its horizontal component. Now, is that horizontal component of that, is that going to be shear stress, or is it going to be pulling or pushing on it? Is this going to be shear here? It's going in that direction. It's going in this direction. Let's use a different color. What could we call that direction? Is that going to be shear, or is that going to be tension? Is it tension, compression, or shear force? Shear, yes, well done. If you can find that horizontal, that could be the shear force. Don't forget, we've also got this. All right, we've also got that. Oh, what have I done? Hang on, boys, I've done something here. What have I done? Oh no, I've made it. What have I done? Sort of zoomed out my own here. Oh no. Hang on, lads. Oh no. I've zoomed out on my blimmin' Apple thing here. So hang on, lads. Take presenter. What have I done? What have I done? What's going on? Sorry, lads. Let's see if I can do this. I've done something. I don't know what I've done. Here we go. Make that. Oh, sorry, lads. I've pressed a button, so it's all gone funny with me. Right. I think I'm back on. Can you still see me? Can you still see me? I've done something other I've done, yeah. Anyway. Right, obviously, if we look at the horizontal, right, that would give me my shear. Now, if I worked out the other one, what would that give me? What's this one here going to be? What's that one there going to be? Is that going to be tension or compression? Tension, well done, Callum. It's pulling on the bolt. So this bolt has got tension and shear. Because this is going up. So this is going up. This is directly on the bolt. It's going up. That's tension. It's pulling on that bolt. This force here, whatever it is in a bit, is horizontal. It's shear. It's trying to shear the bolt off. So that 200 kilonewtons is going to try and shear the bolt and pull it out the hole. What do I need to give you? What do we need to work up this force? What do we need? What have I got to give you? Give you a quick hint, like hint. An angle, right? So let's just say we've got this bolt, right? It's 200 kilonewtons coming like that. We need to calculate the direct force, which that just means the tension, because it's pulling. Look, this is the direct. It's directly on it, and the shear force, which is this. So that's going to be the vertical, and this is going to be the horizontal. Right? So I've got 200 kilonewtons, like we've done in the previous thing, right? We need to break this down into horizontal and vertical. The horizontal will give us the shear stress because it's going in that direction. And the vertical will give us our direct tension. It's pulling straight on the bolt. 200. Callum's quite right. We need an angle. I'll give you an angle of, I'm not going to give you 45. Let's do 30. So all that means is this, that I've got a force now of 200 kilonewtons like this. And I need to work out this horizontal and this vertical with my angle in there, 30 degrees. To find my horizontal, like we've done in the previous with the vectors, right? Horizontal is going to be F cos of the angle. That's going to be cos, and this is going to be sine. So horizontal, which is this force here, which will be our shear, is going to be F cos of the angle. Always, 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 always. What's F? Well, F is 200. Just 200. And the angle is, what do we say, 30. 30. Whack that in your calculator, and that will be the force going in the horizontal direction, which is the force in the shear. Just trying to shear that bolt off. 200 cos 30. What do you get? 173. 173.2 kilonewtons. Right, that will do. Obviously, the more you can put in, well done, Lewis, right? Yeah, I'd go Lewis's 205, yeah. So that's the horizontal force. So that's the force really going this way. That's the force trying to shear this bolt off. Right? Because the bolt, if it works, it's going to shear it and pull it out. So now, the vertical one, what's the vertical one going to be? Well, that's this one. This is the one trying to pull it up. That's going to be F sine. What's the F going to be? The F is still 200, isn't it? And sine of 30. 100 newtons, there we are. Sine of 30 is half. Always check that. That just means there's a force trying to pull this thing out, causing a tensile stress on it to 100 kilonewtons. So I'll just draw this a bit better. So what we've got is, we could have a bolt in Daniel Greenshields. This is the bolt that's keeping everything together. For some reason he's only done one bolt. So, and here's the bolt. Kilonewton is 10 to the 3, yes. Yeah, Kn is 10 to the 3, yeah. What's the matter? What's gone wrong here? Is there anything wrong, is there? 200 sine, 200 kilonewtons, 200 kilonewtons. Well, you've got to put the 200 in. 200, you could put the kilonewton if you want to. You get the same answer. Sine 30. (200) times by sine of 30. (173.2). Well, if you put 200 in there, it will, yes. I've left out the 200. I've left out the K there. It just makes it a bit easier. Saves writing it in. It is K done, right? So in there, strictly speaking, that should be 200 times 10 to the 3. I just write it in, look, and then remember to put it in at the end. You're right, you should put it in, really, because if you forget to put it in, you just end up with 173, wouldn't you? But I don't put it in. I should do, really. It just saves writing it, as long as you know at the end is killer. I mean, you could, yeah, it's the wrong way, really, because you could forget and make another mistake, can you? So that's the bolt, right? And what happens is we've got that's the thing, all right? So what's really happening now is due to this different color, due to this angled force of 200 at, was it 30 degrees, right? What's really happening, this bolt now has got two forces trying to get it. Right, it's got a force now going this way, shear force going that way, which we worked out to be 173.2. 173.2 kilonewtons going that way. It's also got a force, direct, tensile force trying to pull it up of, what do we say, 100 kilonewtons. So this poor bolt now has got two forces it needs to cope with. It's got a shear force. This is shear. Right. Trying to shear it off. It's trying to break it in here. And then this one is trying to pull it. So that's tension. Tension. That's trying to pull it up. This is shear force. Shear force. This is tension. That's also a force. So we need to work out now, is this thing, what's the stress in each direction? Right, we'll just consider one bolt for now. If I had 5 bolts, if I had 5, I could do something different, couldn't I? Right, I consider one bolt. We've got one bolt, right? Daniel is trying to cut corners. He's only going to buy one bolt, right? If I had, you know, 2 bolts, what could I do with that force? Divided by what? Could I perhaps say divided by 2? So you could say then each one's got 100. Right? If I had 3 bolts, you can divide that by 3. It's up to you. Okay, one way you can do it. So then you've got an angle. We've worked out the force now using that 200. All right, 1 bolt. That's why we only use the 200. So we can work out now what is, calculate shear stress don't forget, it's just force over area, shear stress, and direct stress. Now all that means is that direct stress just means really this. It's directly on the bolt. So that's the direct one. It's directly on it. Direct. This force is directly on that bolt. It's going up, it could be coming down. It's direct. Don't forget the force, right? Shear stress, direct stress is the same force over area. Force over area. What's our force? Well, for the shear stress, it's going to be this, isn't it? That's going to be 173 because we're doing shear stress. This is the shear force, 173. So for direct stress, which is this, the tension, right? It's going to be 100. Is it going to break, do you think? We don't know this material, but there's more force trying to shave it off in there. So we've got the forces, right? I now need the area. So Daniel, what bolt have you used? What size bolt have you used? Oh, for plenty. 2 mil. You've used a 2 mil bolt. Okay. Shortcutting all the way. So, in his cost cutting exercise, Daniel has used a 2 millimeter diameter bolt. It's even worse, we've only got one bolt. Don't forget rivets, by the way, lads. Rivets aren't that big, rivets. That's why I've got loads of them. So we'll stick with Daniel. He's got 2 mil diameter bolt, which means we need to calculate the area. It's going to be the same area regardless. So area, it's just going to be pi d squared, isn't it? Pi d squared over 4. So shear stress, force over area. We know the force. We know the area in a bit. Direct stress, tension. We know the force is up here. We know the area in a bit. So over the page. Area. Area of bolt. Daniel is doing really, really cheap. So diameter 2 mil. So we need to convert that to meters, so divide it by 1,000. And area of a circle, pi d squared over 4. Or pi r squared, is up to you. So the area is going to be this. Pi times by 2 over 1,000 squared divided by 4. Daniel, you can take full responsibility for this. What's the answer? You're the one who designed this plane, and the other one's going to be locked up. What are your calculations? So, it's the area of the bolt. Daniel's 2 mil. So 2 divided by 1,000. Square that times by shift pi. Divide that by 4. What you get? Daniel Greenshield's bolt. Somebody type. My pi d squared over 4. 1 point. I don't get that. I don't get that. Try again. 2 divided by 1,000. The square. By the square. Times by shift pi. Divide by 4. There we are. 3.14. Something like that. Yeah, and that. Times 10 to the minus 6 meters squared. That's the area of his one bolt. It's a rivet, really. Very, very small bolt. Right? That's the area. That's what we're going to use. So first of all, we need to calculate now, because we're air crash investigators, shear stress. Shear stress, don't forget, it's the same formula. Force over area. So the area we know is this. The shear force is going to be shear stress, right? Force. So the shear force is 173.2 kilonewtons. 173.2. That's the force. I was trying to pull his bolt out. 173.2. So 173.2. Don't forget the killer. Divided by the area, which is 3.14 times 10 to the minus 6. This will give us the shear stress, right, on this bolt. 173.2 kilonewtons. Don't forget the kilo. Divided by 3.14 to the minus 6. That's the area of Dan's brilliant bolt. Flipping hell. Whew. What's the answer? Connor Richards, Colin Backhouse, Benjamin, Archie, Alex. What's the answer? Very, very small boat. Yeah, there we are. 55 point. That'll do. All right, 55. Let's go to 0.2. Let's make him really, really bad. 55.2 times 10 to the 9 Pascal. Flipping out. 55.2 gigapascals. That's the stress. That's the shear stress. There's something like this on YouTube, yes. This is being recorded, by the way, so this is being recorded, Lewis. This question really is going towards merit. This is going towards the merit now, right? So, this is going towards the merit. If you want to go for merit, you need to. Yes, there'll be stuff. Yeah, so this will be recorded, Lewis. Or you'll have the notes anyway. I put the recordings up. But yeah, this is like a merit question coming now. So, all right, that's the shear stress. 55.2. Now we also need to work out. So we know the stress in that direction, we just worked it out. Now we need to know what the tensile stress is. It's still going to be force over area. What's the force? 100. Daniel's bolt is still the 2 mil one. So the direct stress, that just means tension or compression. It's directly on the bolt. That's all that means. It's directly on it. Still force over area. Still force over area. Force over area. What's the force in the direct? That's tension, right? We've got it in tension at the moment. What's the force in that direction? Where is it? 100. Don't forget, it's killer. All divided by the area. It's the same area. Dan's dodgy bolts. 3.14, so it's pi times 10 to the minus 6. It's the same area. 3.14 times 10 to the minus 6. This will give us the stress, the tensile stress, really, because it's trying to pull it in it. So it might snap this now, might not. We don't know yet. 100, divide that by all of that number. That's what you boys are doing. Delete 6. There we are. Press E and G, right, because your calculator may give you to the power 10. So you might get this. Your calculator will give you this actually. 3.18 times 10 to the 10. Right, this hasn't got a symbol, so press E and G. You can move it 1. 318 times 10 to the 9 pascals. 10 to the 9 is giga. 3.18 gigapascals. So we now know that we've got a stress in this direction. And we've got a stress in this direction. Let's find out, is this safe, right? So I'll just quickly draw this again. There's that, and there's that. Our bolt was here. We've just worked all that out, right? There was a force on it, like this, 200. And we worked all that out. And in the end, we worked out that there was a stress going this way. That's all it is. A stress going that way, because there was a force going that way. There's also a stress going this way, say. There was a force going there, and there was a force going there. We worked the area out of Dan's dodgy bolts. Gave us a shear stress and a direct stress. The shear stress was 55.2 giga. So 55.2 gigapascals. That's shear. That's how much stress is trying to snap this bolt. It's also got a direct stress up here, which is tension. It's trying to pull it, which was tensile stress. It's directly on it, 31.8. 31.8 gigapascals. That's direct. It's directly on it. In this case, it's tension. Tension. Flipping I won't come onto your plane, Daniel Greenshields. Sheesh. So let's pretend. Let's pretend now, right? This bolt has got ultimate tensile stress, right? Ultimate tensile stress. Now this bolt is going to break at, right, 500 megapascals, right? So when this bolt is under a stress of 500 megapascals, it's going to break, right? So is it safe in that direction? And I'll also give you, this bolt has also got ultimate shear stress. Ultimate shear stress of, let's say, 750 megapascals. That just means if the stress in the shear direction is near 750 megapascals, it's going to shear off. So we can work out now the safety factor in tension and the safety factor in shear. Don't forget, if it's below 1, we're all dead. Apart from Daniel Greenshields, who's probably jumped out of the plane by now. So, safety factor in tension. Safety factor in tension. So safety factor, SF, is safety factor. Don't forget the safety factor is going to be the ultimate, what it's going to break at, all over what we're working at. We're doing tension now, right? This is tension. So is it safe in the tensile direction, which is up and down? Don't know. Don't know yet. The ultimate tensile stress is 500 megapascals. So it's going to break when it gets to 500 mega. Hopefully you can see that it's not safe, right? It's going to break at 500 megapascals. There, look, ultimate tensile stress, 500. It's going to break at 500. What is the stress that we've worked out due to this force on this bolt that he's trying to cut corners with? This is why it has happened, by the way, when people cut corners, and you know, that's why it works, happens. We know there's 31.8 gigapascals going in that direction. Holy moly. 31.8 times 10 to the 9. This will tell us if it's safe or not in the tensile, in this direction. Is it safe? Is it safe? 500 mega. Don't forget to put the mega in. Divide by the killer. Sorry, the giga. Or the giga. What do you get? What's the safety factor? Daniel Greenshields? You conning person? You've designed this plane with a safety factor of, come on, what is it, Dan? I'm going to name and shame you. I'm going to get you on TV. 500 mega divided by 31.8. Don't forget, Lewis, this here is giga. 0.0157. I thought Daniel had gone all shy then and tried to scarper and left the country. That's how Daniel Greenshields gets on with it, just make things up. Obviously, is this safe? 0.0157, no, is nowhere near. That bolt is going to be good night. Bang, snap. In that direction anyway. In this direction. Yeah, name and shame. We have on BBC One, 10 o'clock in the afternoon. Now, let's find out, is it safety factor in shear? Let's see if he's all right. Because it may just hold it. It didn't, but we know now that it's going to break. Right? It's going to break in this direction massively. Is it going to break in this direction? Right, okay, this is shear. We know the shear stress is 55.2. And we know it's going to break at 750. It's going to break at 750. So, safety factor. So, safety factor in shear is again going to be the ultimate overworking. The ultimate, what it's going to break at, it's going to break at, right, in shear, what is it going to break at? It's going to break at 750 megapascalios. In shear now, 750. So it's a bit stronger in shear. But it's not going to make no difference whatsoever by the looks of it. 750 megapascals shear is going to break shear stress, look, ultimate shear stress of this bolt, 750 mega. What's the shear stress? Well, it's 55.2 giga. .2 giga is 9. I think we're dead in both directions, right? Type it in, right? Obviously, it's miles, right? Because it's going to break at 750 mega, but we're going at 55.2. Naught point 0.013. It's even worse. No 0.013 in the so the safety factor is 0.013. So it's going to shear off due to this force on this small bolt. It's going to shear off. It's going to snap. And it's also going to snap. The bolt's going to snap off and shear off. Sounds all right to me? Yes, it does sound all right to me. No, what's wrong with it? What would you suggest Daniel does? What do we suggest Daniel does? Close down, quit, move to Vietnam. Take your cash. I wouldn't trust him to move to the moon because whatever, right? Obviously, the 2 mil bolt could be the reason. We've only got one of them. So Daniel, I would suggest you go and read a book on trading standards. Obviously, we've got a we've only got a 2 mil, 2 mil diameter bolt. That's 2 mil. That's life size. Look, not even life size. Is it? 2 mils. Yeah, Tichy 2 mil. Not even that. Can't even draw it here. Not big enough. 2 mil diameter. Come on, Dan. So you either go more bolts, bigger bolts, less force, whatever you want to do, but it's not much 200 kilonewtons. It's the bolt is where your problem is. That's where the problem is. Right? That's where the problem is. Now, like I say, boys, this is going towards, this will help you in the merit. Don't forget the merit question is a bit more thinking and a bit more, all right, so we've covered a bit on it. Right, the merit, when you see, we'll have a break in a bit, right? And I'll show you the assignment. We'll have a break for 15 minutes. But the passes, right, are fairly alright. But the merit question has got a bit of this stuff in it. Right, so we have a break for a quarter of an hour. When we come back, I'll show you the assignment. I'll show you the assignment. Some of you have already done the beam one. It's issued now, yes. It's on Moodle right now. I'll go through it though, Ty, right? And then perhaps you could do, you've done the beam one already. Perhaps you could have a go at, so we'll have a go at some of them in the class. No, it's there's a pass, there's passes and merits. It's on Moodle right now. It's under, don't go to the enhanced one because you'll have different numbers. You've all got different numbers, see? But well, you'll see now in a bit, Callum. There's 3, 4. There's 4. There's vectors, there's a beam, there's a couple of stress ones, and there's a merit, which is like this with an angle and 3 bolts or something like that. Let's have a cup of tea and a sandwich. I'll come back at 1:45 and I'll go through it with you. Okay, some of you should have already done the beam one. And I'll let you make a start on the stress ones. No, come back at 22 now, Alex. It's on Moodle, Callum. Come back at 1:45. 2:45. I'm going. Mute.